All right, well, hello everyone and welcome to part 3 of our videos on the chapter 8 material, where we're going to continue to look at addition across a carbon-carbon double bond. In the last video we looked in some detail at the addition of the hydrohalide acids across a carbon-carbon double bond, so HCl, hydrochloric acid or hydrobromic acid HBr, and looked a little bit in sort of the regiochemistry of that reaction and a little bit of the mechanism underlying it. In this video, what we want to take a look at in some detail now is another very similar reaction where we're going to take a look at acid-catalyzed hydration across these double bonds. And so the outline of the reaction is shown here, where we have a double bond that we add a molecule of water across that double bond. So we're really hydrating that. That's where the hydration comes from. We need some acidic conditions to be able to do this. And really, if we're looking at this mechanism, and if we're looking at this reaction, it really does look like the reverse of E1, and I've drawn it with reversible arrows specifically to point that out, and we'll take a look at that as we look at the mechanism here in some more detail. So let's start by looking at that mechanism. So we have our carbon-carbon double bond containing species, and again, I'll just draw an H plus here. We know that doesn't really exist on its own. We'd think of that more as H3O plus. And we think of that carbon-carbon double bond acting as a nucleophile. That's a lot of electron density between those two carbon atoms that we can use to carry out some kind of a reaction. And so here I'll draw in equilibrium arrows that opening up of that carbon-carbon double bond to form a carbocation. And so now we're at the stage where we can look at that and we can understand exactly which carbocation we would predict to be the major product observed here, that stabilized tertiary carbocation. And now the mechanism, and this looks familiar, hopefully, quite a bit from what we were drawing earlier when we were looking at the E1 and SN1 reactions. We've got a carbocation now that's formed. We have attack of that carbocation by a nucleophile, in this case a molecule of water. And we know quite a bit about how good, or more correctly, how bad that is as a nucleophile. That generates a species that looks like this. We've got that proton on there still, so we've got a full formal positive charge on that oxygen. And then here we can bring another molecule of the water in, of course the solvent sitting around there, to pick off one of those protons and leading us directly to the product. And again, as we've seen with hydrohalogenation, the steps of the mechanism are identical, reverse to what we observed with the elimination reaction. And so here I think is very familiar ground for us. And so we've proposed in this particular mechanism the intermediacy of a carbocation. What evidence would we have for the production of that carbocation? Well, similar to what we had for the unimolecular mechanisms in substitution and elimination, we can do similar kinds of evidence here for that carbocation. If I take a substrate that looks like this, and if I expose it to conditions where that double bond would be hydrated, so H plus and H2O, again, just an excess of protons and water, the product that we observe would be a racemic mixture here. Be a racemic mixture, and of course the carbocation that we would propose as the intermediate here, with that phenyl ring, that aromatic benzene ring, phenyl ring underneath there to stabilize that, and then we would draw something like with a methyl going back and that ethyl coming forward. And of course we've got that unhybridized atomic p orbital sitting there, and either side of that atomic p orbital, that incoming nucleophile, in this case of course the water, can attack from either direction. This looks almost identical to something that we drew when we were discussing the unimolecular mechanism for substitution some time ago. So we observe a racemic product, and of course that's because we get the intermediacy of that carbocation. I'll put my positive charge on that carbocation just for those of you that like to keep track of that when you're looking back on this. So that's the evidence. We get a racemic mixture as well. So one other note we'll make about this reaction, and the note applies to sort of the idea that we have two possible outcomes of that carbocation. We can either get an elimination or a substitution if we form that carbocation. Are there things that we can do to influence the outcome? So for example, if we have something that can form a double bond, and we're trying to compete with something that forms that tertiary alcohol, and we've got a molecule of water here, we can do things to influence the outcome. Now, we talked at the start of the substitution chapter about the influence of temperature on the reaction, so we'll touch on that very briefly. But here, for a given temperature, so that implies that we're at equilibrium. What things could we potentially do to influence the outcome here? Well, we have a molecule of water as part of the reaction, either in the way that we've drawn as part of the reactants together with the double bond to give the alcohol, or if we start from the alcohol, it forms part of the products if we're making the double bond, depending on which direction we run this. So at equilibrium, we can take advantage of the presence of that molecule of water to try and influence the outcome of this reaction. If we do this reaction in dilute sulfuric acid, so dilute sulfuric acid implies that there's lots of water present. If we put lots of water into the reaction at equilibrium, it will shift to take into account that extra water being present. So something similar to Le Chalier's principle that we might have talked a bit about in general chemistry. Adding water to the reaction would favor, in this particular instance, for it to go to the tertiary alcohol product. Likewise, we could influence it going the other way if we do the reaction in the presence of concentrated sulfuric acid. So concentrate very little water, or almost no water here, then that would influence the reaction to go the other way to produce the water and drive that reaction to give us the elimination product as well. And I'll make a final note on this, so we can also use temperature to influence the outcome of this reaction as well. And so this is going to be part A of our section 3 on chapter 8 material. We're going to put a part B video up in a minute about hydroboration.